All right, let's do this. We actually get to finish off our discussion of aldehydes and ketones today. I need to go back to this nomenclature business because there's one important thing that I forgot to, that I left out here. And these are our special aldehydes and ketones. All right, there are two, an aldehyde and a ketone, that are just so special that in terms of their nomenclature, we always call them by their common name. Basically, their common name was so widely in use when the IUPAC was first formed that the IUPAC just said, fine, we're going to just take that as the IUPAC name, all right? And that is this one, which I'm sure you're very familiar with from lab, our smallest possible ketone. What do we call this? Acetone. Not 2-propanone. Nobody calls it that. Everybody calls it acetone. All right, and the other is that smallest possible aldehyde that you can have. All right, so where we have only one carbon and two hydrogens. This is not methanal, but formaldehyde. All right, very widely used on an industrial scale. You might have encountered it in a biology class if you ever did any sort of dissection. This is what we use to preserve dead bodies. All right, but these two are so commonly used that our IUPAC name is actually our common name here. These are our IUPAC accepted names. Cool. All right, so last time we were looking at our nucleophilic addition reactions. And we have our two categories of nucleophiles, our basic nucleophiles and our acidic nucleophiles. And both react with that carbonyl group in the exact same way. We have that electrophilic carbonyl carbon that gets attacked, and that pair of electrons jumps up onto that oxygen. All right? So we get our nucleophilic addition product. Here's a good example where we have our nucleophile added to what used to be our carbonyl carbon, and our carbonyl oxygen is now this hydroxyl group. And most of our nucleophiles were just overlap from what we've seen before, but we did make a special category this time for nitrogen nucleophiles. And we called these instead nucleophiles that will react not under acidic or basic conditions, but under neutral conditions, which truthfully was slightly acidic, but the important part here, the important distinction, was that in our intermediates, we saw both positive and negatively charged intermediates, and that was okay, right? The other thing that was weird is we didn't just get our nucleophilic addition product that we would expect with that hydroxyl group on there and our nucleophile added. That was an intermediate in this reaction, but it kept on going from there, right? From there, we actually kick off that oxygen as a leaving group, and what we're left with was what we called an imine, right? This nitrogen-carbon double bond. So notice, and we said that this was only for primary amines and ammonia. So notice that in this case, we lose two of those hydrogens in order to form our two new nitrogen-carbon bonds. All right, our imine product with our primary or ammonia. And then we said we were going to do secondary amines this time. All right, so we're going to do the same thing as we did before. I want you to see if you can't give me these first two steps and get to that expected product, that carbonyl amine. All right, our nucleophilic addition product that we would expect when we stick a nucleophile in with our aldehyde or ketone. All right, and remember, these are these neutral conditions. So this intermediate right here in particular will have both a positive and a negative charge in there. So that first step is that nucleophilic attack to that electrophilic carbonyl carbon. All right, we get our tetrahedral intermediate here, where we have that alkoxide ion, as well as this nitrogen here with its two ethyl groups. That nitrogen still has that hydrogen on there, which means that it also has a positive charge. All right, so this is this intermediate we said can only exist under these neutral conditions here, because it is both a negative charge and a positive charge. That is a very annoying ring. Yeah, definitely will wake you up. So now we need to, this thing's all pissed off, right? It's got a positive and a negative charge. We need to go ahead and satisfy everything. We could do this in 2 steps if we want, or we can do the lazy man's 1-step proton transfer here. This makes oxygen happy and neutral, as well as my nitrogen happy and neutral. Nitrogen gets its lone pair back. Oxygen gets its complete I guess it had a complete octet before. It gets its formal charge at 0. All right, and this is what we said we would expect to get, this intermediate here. This is what all of our other nucleophilic addition reactions gave us. But again, nitrogen's special. We put it in this special category here. This is going to continue to react in such a way that we're going to kick off that oxygen, just like we saw before. But again, we need to turn it into a good leaving group. All right, so we're going to convert oxygen, OH, into a good leaving group. Whoops. By protonating it, right? That same strategy that we've seen before on terms of converting a hydroxyl group into a good leaving group. So this is where our slightly acidic conditions come in here. We have these hydronium ions floating around that can donate protons to that oxygen. So here is our protonated carbonylamine. And again, we said we're going to break this bond, right? That's the whole idea, is we're going to kick off that oxygen. But where does the impetus to kick off that oxygen come from? This carbon's not going to violate its octet rule, right? So where does that come from? It's that pair of electrons on that nitrogen that comes down and kicks off that oxygen leaving group. And so up until this point, we have exactly what we saw in our previous mechanism with our primary amines. All right, we have this carbon-nitrogen double bond. All right, so here's now where we're at. We got to this same place last time. The difference was because it was a primary amine that we had started out with, it had this extra hydrogen that we could just pluck off to remove in order to create our neutral product here. Well, if we look here, we don't have any such hydrogen to remove because we started out with a secondary amine. All right, so how is this thing going to get nice and stable and neutral? Again, we're going to need to remove a hydrogen. The tricky bit is that it doesn't come from this nitrogen. It comes from a neighboring carbon. And it's going to look a lot more like an elimination type reaction here. All right? There's going to be some base. We'll use water. Is going to grab that proton. Again, we're going to remove a proton here. But that pair of electrons in that carbon-hydrogen bond comes down to satisfy this carbon's octet so that nitrogen can get back its lone pair of electrons. All right, so what we're left with is not a carbon-nitrogen double bond, but a carbon-carbon double bond from that formerly carbonyl carbon and its neighbor. All right. This one used to be our carbonyl carbon. All right, and don't worry, we got a fancy name for this one as well. This one with its carbon-carbon double bond, that ene ending, and its nitrogen, which I forgot its lone pairs, is what we call an ene-amine. All right, and so here's our enamine formation reaction mechanism. Okay, just to summarize for our nitrogen nucleophiles, again, we put this into a different bucket than our acidic and basic nucleophiles. If we take, we always use acetone. Let's do cyclohexanone. All right, let's just summarize this here with an example. Everybody give me the product if we treated cyclohexanone with this primary amine versus if we treated it with our secondary amine. All right, so I'm going to pick up my amine here and I'm going to attach that nitrogen to that carbonyl carbon, but I'm going to have a carbon-nitrogen double bond. All right, and then I have that 4-carbon tail here, that little isobutyl group sticking off. All right, with my secondary carbon, my secondary amine. Again, I'm going to attach that nitrogen to what was formerly my carbonyl carbon. But now that carbonyl carbon has a carbon-carbon double bond with its neighbor. All right, and my nitrogen still has its two methyl groups. Okay, and so the distinction here was in the first one we were using a primary amine. That gave us this imine with an I. In our second one, we were using a secondary amine, and that's what gave us these enamine products. Okay, and we wanted to put nitrogen nucleophiles into a separate category from our normal nucleophiles. All right, let's just do an example here so we can see how this differs. All the other nucleophiles in the world behave in a much more simple manner where we take that, in this case we'll use this same ketone, we add in that nucleophile. Depending on our nucleophile, we would either have our mechanism be under acidic or basic conditions, but in terms of our product, it doesn't make a difference. In either case, acidic or basic conditions, we would just get our simple nucleophilic addition product. All right, where that carbonyl oxygen has stuck around as a hydroxyl group. All right, so we have our normal nucleophilic addition reactions. These are what we discussed first with our reactions of aldehydes and ketones. We made a big stink about how that electrophilic carbonyl carbon is like the key to understanding these reactions, all right? And then we said, all right, but if you use a nitrogen nucleophile, something kind of weird happens. Everything starts out exactly as you would expect. You get this nucleophilic addition product. But then it keeps on going from there and ends up kicking off that carbonyl oxygen to form either your imine or your enamine, depending on what type of nitrogen nucleophile you use. All right. Well, now we're going to look at a very specific reaction involving nitrogen nucleophiles, what's called a Wolff-Kishner reaction. All right, so let's take a ketone here, butanone. All right, and we're going to use a primary nitrogen nucleophile here, but we're going to use a very special one, what's called hydrazine. We'll draw out our chemical formula here. All right, so this is when we have these two nitrogens single bonded to one another. I guess it's not technically an amine because there's no carbons in there. This is hydrazine, all right? But it's going to behave much like a primary amine because it's got those two hydrogens that it can lose. So everybody take a second and give me our product here. So we get our imine product here with that carbon-nitrogen double bond. All right, I guess it would be good and put in my lone pairs. But a Wolff-Kishner reaction is when you do this nitrogen nucleophile, especially using hydrazine, and then you follow it up in a second step with potassium hydroxide. Because what that ends up doing is cleaving that nitrogen carbon double bond, and what you're left with is just a fully reduced carbonyl carbon. All right, we have chopped that carbon-nitrogen double bond and replaced it with just 2 new hydrogen atoms, right? We have fully reduced that carbonyl carbon using this Wolff-Kishner method. All right, so Wolff-Kishner, this is how we can fully reduce a carbonyl carbon. All right, remember by reduce, I mean adding new carbon-hydrogen bonds. So now we have fully reduced this carbon here so that it doesn't contain any carbon-oxygen bonds. Okay, so if we just want to use our example that we've been kind of using to help summarize our reactions here, if we want to summarize our Wolff-Kishner reaction, it would be first treating our ketone or aldehyde with hydrazine, and then in that follow-up step, use that potassium hydroxide. And so everybody take a second and give me what my product would be. Again, if we fully reduce that carbonyl carbon, we've turned cyclohexanone into just cyclohexane, right? This process effectively just cleaves that carbon-oxygen double bond. All right, that's our Wolff-Kishner reaction. We got one more named after a dude. This is a Wittig reaction. Right, these Wittig reactions use a Wittig reagent. It's called an elide. And that is when you have phosphorus double bonded to some organic chain here, some R group. All right, but that phosphorus is also bound to 3 phenyl groups, 3 benzene rings. Right, so this is our Wittig reagent, an elide. And they're kind of a pain in the butt to draw. So instead, you'll typically see them as R, whatever that alkyl chain is, P, pH3, right? And that pH stands for those 3 phenyl rings. You don't have to, but you will because of the program. You'll see it drawn out, but you yourself do not have to draw it out. All right, so how do these react with our aldehydes and ketones? All right, so let's take a ketone here. We're going to react it just with our simplest halide at first here. All right, so our carbon in our halides has a lot of electron density here because phosphorus has this expanded octet. All right, so this is another example. Let's just note, well, let's do it in red. Got lots of electron density. So this is another example of a carbon nucleophile reaction. We've seen other carbon nucleophiles, notably our Grignard reagent, as well as our cyanide ions. All right, and those react with aldehydes and ketones as well in our very normal nucleophilic addition reactions. These Wittig reactions, we're going to put them in a separate category here because those don't do the exact same thing. Yes, carbon's going to play the role of a nucleophile. It's going to attack that electrophilic carbonyl carbon. But then there's this weird rearrangement that happens. So what you're left with is a carbon-carbon double bond, where my carbon in my Wittig is now on the other side where my oxygen used to be. All right, so with Wittig reactions, we have a carbon nucleophile, but we form a new carbon-carbon double bond. All right, so let's take our cyclohexanone here. All right, we want another example. All right, so we're going to take that carbonyl group, and instead of having a carbon-oxygen double bond, we're going to have a carbon-carbon double bond. All right, and I need to include all 1, 2, 3 carbons from my Wittig reagent. All right, but we're going to make a new alkene from our ketone here. All right, so we have this Wittig reaction, another carbon nucleophile, but we don't want to lump it into the same category as all of our other carbon nucleophiles because we don't get that normal nucleophilic addition reaction. Instead, we get this carbon-carbon double bond at the end, replacing our carbonyl oxygen with whatever on the other end of that Wittig reagent. All right. So aldehydes and ketones are actually relatively well behaved in terms of their reactions, or at least at this point. Don't worry, we'll complicate things in a future chapter. All right, but at least at this point, really the only thing that we were focusing on was that electrophilic carbonyl carbon, right? That's the key to understanding the reactions of our aldehydes and ketones. It's going to be an electrophile. Some nucleophile is going to attack it, right? And this is going to be true. We're going to see a lot of other carbonyl-containing functional groups. And this part right here is the exact same for all of them. They're always going to be attacked, these trigonal planar carbonyl carbons, and forming these tetrahedral intermediates here. Okay? And so that was our key here for this chapter. Then we just sort of, in this case, we protonated that oxygen to give us that alcohol group. So we had our nucleophile attached as well as our alcohol group. All right? We said we're going to get into a good habit next time around, and we'll see why. Is there a good leaving group? And in this case, the answer is always no, right? So we keep both our oxygen and our nucleophile, attached to the same one. So that's true for all aldehyde and ketone reactions, right? That electrophilic carbonyl carbon. There are a few weird ones that we kind of set to the side, because after that happens, some other weird crap happens. So for example, our nitrogen nucleophiles, right? Everything starts off normal. That electrophilic carbonyl carbon gets attacked, but then this rearranges itself again to form either our imine or our enamine. All right, and then we have our Wittig reactions. Again, it sort of starts out just as normal. We don't have a mechanism for this one, but you can trust me that it kind of starts out normal with that nucleophilic carbon attacking that electrophilic carbonyl carbon. But again, then some weird rearrangement happens. So again, we're going to put these Wittig reactions in a different category in our brain as well. All right. The other thing that we kind of threw in this chapter here was our nitrile reactions. All right, which is you can use that carbon nucleophile and you get your nucleophilic addition product, nothing different there, right? It's just then you can take that and do another step with it. Actually, two different things you could do with it. You could either reduce that nitrile group to create an amine, or you could oxidize it with just acid to create a carboxylic acid group. So these were kind of two extra reactions that we threw into this chapter as well. Just a normal old nucleophilic addition reaction, but then we just said, oh, look what we can do with that product. We got these two new things that we can do. All right? Likewise, with our nitrogen nucleophiles, we kind of threw in a special one in there as well, these Wolff-Kishner reactions. At first, we just get our normal nitrogen nucleophile reaction. Well, not normal, it forms that weird imine product. But if we take it and we follow it up in a second step here, now we have this method of reducing that carbonyl group fully, right? Making it not just an alcohol, the first reduction step, but fully reducing it so that we actually get an alkane as our product. All right? And so those are our reactions of our aldehydes and ketones, and that's that for chapter 19. Okay? Cool. So I'm done. Importantly, on Friday, that would be really fun to start in our next chapter. But I think what would be even better is to give you that day to catch up on your homework so then you don't have anything to do over spring break. All right, so we don't have lecture on Friday. Wonderful.